In an impact, the first couple of milliseconds are the most critical ones.
People have to understand the concept of injuring the brain through rotation.
Now, if you would watch a slow motion video of a boxing match where someone gets hit on the chin, you will see that the skull with the teeth instantly rotate, while the nose, the ears, soft tissues stay back and get distorted. Unfortunately, inside the skull, the same happens, where the skull quickly spins, but the brain gets distorted, causing the injury.
There's a number of testing standards that exist for helmets already. They're all linear drop tests.
The simulated head is dropped straight down on a flat surface, and it's rigidly mounted that the head cannot rotate. So we need to modify that impact tester to allow for a more realistic impact, meaning oblique, and then we added a neck surrogate to it, so now the head can rotate during impact.
When we first looked at this and we thought about that, we started testing this, and the first thing we went to obviously was a slip layer. Slip liners at low energy reduce the amount of rotational acceleration in the system, but as you start to increase the energy, their efficacy starts to decrease.
What can I make to lessen that rotational spin to the head during an impact?
Michael introduced the concept of a material that was three-dimensional and could start to behave in different manners depending on the angle that the energy came into, and it's that whole process that led to WaveCel.
WaveCel structure has a specific cell shape that makes it deform into a sphere without distorting the cells. Using a continuous liner is suspended inside a helmet.
It behaves differently depending on the angle that it's hit at, which is very unique to the material.
Each cell has a small fold in it that helps in initiating the crumpling for the straight impact, but most importantly, it allows the cells to fold over in shear.
And would allow the helmet to spin on itself rather than imparting that spin to the head to cause the concussion. If you take a standard force and a threshold at a given angle of impact, you can calculate what your risk of concussion would be.
The standard foam helmet reduced the injury risk to about 53%, while adding the WaveCel technology reduced it to only 1.2%. The beautiful thing about research, it's really open source and collaboration based. We conduct the impact, we measure the forces, we send those data to France and they can simulate what would happen to the brain. We look at other aspects that could be of concern, such as skin abrasion, and a consistent feedback we get is how comfortable those feel. Your regular EPS helmet, it's a hard rigid shell, so you have pressure points, but WaveCel is a flexible dome inside your helmet that naturally conforms to different head shapes.
Because it's pretty much all air, it's extremely breathable material, and from a convection standpoint, it lets out a lot of heat and air can flow through it.
Having production locally here in Portland allows us to do a lot of on-site testing for impact, for stretching, optical for coloration. Then we want to look at different impact angles, different impact speeds. Then we go into cold condition, hot condition, aging, UV impact. So it's a fairly intense process. We can ensure on-site that WaveCel leaving our facility meets all of our requirements in a consistent manner.
Developing a better helmet that decreased concussion sort of gave me and Michael the opportunity to explore that realm of prevention.
It's a very straightforward strategy in a research endeavor to develop the best helmet we possibly can. We will produce more papers in the future where we look at all the new technologies, how they work, and hopefully just inspire change, advances. I think there will be great opportunities going forward.